Let's move on to differential privacy. The differential privacy, let's be careful about the setting, because in security and privacy, it's always very important to be precise about the setting that we're working in, what the threat model is, what the adversary can and can't do, and so on. So let's be a bit careful here. So we work in the following type of setting. We have n individuals, which each have their own data. So we're kind of going to use them and their data points interchangeably. So the first data point is x1, x2, so on, all the way up to xn. And these data points, and these are the data points which belong to the individuals, there's going to be the presence of an individual which we call the trusted curator, or just the curator for short. And why do we call them the trusted curator? It's because they're trusted, I guess, by the users, in the sense that user I, they don't want their data point to be shared with anyone except for the curator. They trust the curator, but no one else. So you can picture them sending their data here. And what the curator is going to do is they run an algorithm M, sometimes called a mechanism in differential privacy for whatever reason. Yeah, it's not the greatest name, but yeah, they have some algorithm M, and they output M on the overall data set x1 through xn. So what do I want to comment here? Essentially, where's the privacy barrier? The trust barrier is here, in the sense that what do I mean by that? A trust barrier. I mean roughly that the individuals trust the curator, who's here behind the trust barrier on this side of it, but whatever the curator outputs has to be private, so that whoever sees anything on this side of the trust barrier shouldn't be able to violate the privacy of individuals on this side of the barrier. So yeah, it's time to finally get to the definition of differential privacy. Differential privacy is going to be a property of an algorithm. So for example, M in particular is going to be something that's private, which essentially says that no individual's data has a large impact on the output of the algorithm. That is kind of to say that, if we changed x1, then this wouldn't really have a huge impact on what the output of the algorithm M would be. Okay, and let's be a bit more formal about that. For this purpose, I've copied the definition from Salil Vadan's survey, and I just blacked out a few parts which are not really relevant to our coverage, just to make the notation a bit simpler. But okay, let's read it and see if we can interpret it. So we're going to talk about differential privacy, or for now, this is what's known as pure differential privacy. We'll revisit what it means to have not pure differential privacy. But okay, differential privacy, we say that a randomized algorithm or mechanism M is going to be an algorithm which takes in a data set of size n and outputs something in some space y. We're going to say this algorithm is epsilon differentially private, so notice it's parameterized by something called epsilon. If for every pair of neighboring data sets, x and x prime, so that is, what does it mean for them to be neighboring? They differ in exactly one row. So this is kind of what I said, where, an individual, and if their data was changed, then that's sort of what it means to be a neighboring data set. A neighboring data set is one where you have a data set and a single individual's data was changed, and that's now a new data set which is neighboring. So, okay, we say an algorithm is differentially private if for every pair of neighboring data sets, we have the following kind of unusual guarantee. So let's take a little bit more careful look at this. What does it say? It says for all t, which are subsets of the range of the algorithm. So remember, y is the range of the mechanism or the algorithm, and t being a subset of this range means that it's some sort of event. So for all events that could possibly happen, we're saying that the probability that that event happens under the data set x being fed in is going to be close to the probability of that event under the data set X prime being fed in. So, okay, why is this? And what I said, the two distributions are essentially going to be close. That is like the distribution of M on X and the distribution of M on X prime. What do I mean by close? Well, we're going to use a multiplicative guarantee. We say that the probability of every event is essentially preserved up to this multiplicative e to the epsilon. Okay, so this is a bit of a mouthful, so we're going to spend quite some time trying to digest this and really like build some intuition for it. But just to repeat it one more time, let me say what this is. This says that, if you have two data sets which differ in only one entry, then the algorithm, when run on these two data sets, will have a very similar distribution over outputs. And we quantify how similar those output distributions are in a multiplicative sense, using the fact that for every event, it's going to be e to the epsilon times more likely at most than it was under the other data set. Okay, so this is differential privacy. It's basically the reason why we're all here. It's kind of the reason it sparked an entire field. It was invented by Dwork, McSherry, Nassim, and Smith in 2006. And it's very highly celebrated in a number of different areas, in the sense that, this was originally in TCC 2006, but in 2016 they won the Test of Time Award. They won the 2017 Gödel Prize. So the Gödel Prize is essentially the top prize in theoretical computer science. So it's very highly respected in sort of the academic circles. But that's not it, like in the sense that it's also used far beyond just academics and theory. It's in practice. It's used in practice at companies like, for example, Uber used it somewhat recently. I'm not sure if they still do use it, actually. It's used at Microsoft. It's used at Google. Facebook uses it nowadays too. They're making a big deal about this. And like I mentioned, Apple should also be mentioned. Apple, they're sort of one of the more higher profile ones and used it a few years ago in practice. Also, LinkedIn is working on a deployment. I think they might already have some deployment. I'm not totally sure, but they're working with it. So basically a whole bunch of companies, as well as I've mentioned before, the US Census Bureau is using it for the 2020 census. So this is it seems like this is the kind of this is the gold standard, so to speak, of data privacy right now. It's strongly accepted as a strong notion of privacy. So this is what people are sort of flocking around. Sometimes people like certain variations of it, which we'll talk about, but this is kind of the core definition, which everything else is spawned from. Okay, so that's sort of a bit of a side note. Let's talk more technical stuff. Let's revisit this. And like I said, it's not an easy definition the first time you see it. Like seeing the expression itself is kind of confusing, but hopefully some of the intuitions I gave might help. You're essentially trying to quantify how much the distribution of outputs changes when you change a single element of the data set. And if you can say that it's small, the distributions are in some sense close, then it will be differentially private. So there's a number of technical comments I want to note here. So first of all, this is a quantitative definition. In the sense that, it's parameterized by some value epsilon. The smaller the value of epsilon you have, then the more private it is. In fact, yeah, so epsilon equals 0 is sort of perfect privacy, so to speak. You won't be able to get anything useful in it. If you just sort of look at the definition, you'll see that essentially the distribution under all data sets has to be the same, exactly equal. And on the other hand, every algorithm you studied before this course is infinity differentially private, in the sense that that sort of just degrades to having no privacy guarantee. So it's a quantitative notion where a smaller epsilon corresponds to better privacy. And what is epsilon exactly? Epsilon, like how big should we think of it? It's kind of a small-ish constant. What is reasonable? Say like, you know, say 0.1 is sort of a reasonable lower bound. Getting smaller than that is kind of tough. You might lose a lot of accuracy. And maybe up to say something like 5 is kind of this is a tough question to answer because it's very sort of situation dependent. But generally, I think if it's between these two bounds, epsilon between 0.1 and 5, that's kind of like, okay, nothing too surprising going on here. If it goes outside of these bounds, then maybe you should be a bit suspicious and be just tread with caution, so to speak. One thing I want to note here is that sometimes we think of epsilon as being, in other contexts, as a symbol that's between 0 and 1. Here, epsilon greater than 1 is still a sensible definition. It still makes sense. But be careful because it's exponential in epsilon. So as epsilon grows bigger, then you quickly get weaker and weaker privacy guarantees. Okay, what else do we want to say? We'll also comment that differential privacy is a worst case definition. And what do I mean by that? I mean, I want to contrast this with the statistical setting. For example, often we work in the statistical setting where we have a data set which is generated IID from some distribution. Say, you know, you have a bunch of data points which came independently from some Gaussian or something like that. Well, for differential privacy, we kind of throw that out the window in the sense that we do not assume that there's a distribution over the inputs. In particular, notice how it says for every pair of neighboring data sets. Yeah, for every pair. So that means no matter how unlikely they are, it still has to be worst case over all pairs of data sets, and we need this strong guarantee. There do exist some cases of some notions of average case differential privacy. There's a few pitfalls you have to be sure not to fall in when you're doing these. So yeah, I won't talk about this too much, but there's some very nice blog posts written by two of my friends, Thomas Steinke and John Ullman. And I link these in the lecture notes. Check out their blog posts. I'll probably also link them in the description. Okay, so that's another point. It's a worst case definition. What else do I want to say? I guess I already said this, but let me just reiterate it because I think it's an important point. If you want to explain this in words, the definition essentially bounds the multiplicative increase in the probability of m's output satisfying any event when you change one data point. So that kind of says that the probability of any bad thing or any good thing happening will be at most an e to the epsilon factor more than it was before. We'll revisit this a bit more when we talk about interpretations of differential privacy and what it actually means to, like, say an algorithm is differentially private. What does that mean? What can we take away from that? But we'll revisit that later. One thing you might find a bit unnatural is why that an e to the epsilon here? In particular, you might think that, like, instead of this, 1 plus minus epsilon is more reasonable. This might be, if you're a theory buff, this might be the type of thing you're more used to seeing, where it's like a multiplicative approximation at 1 plus minus epsilon. Well, let me say that this is kind of the same thing. What do I mean by that? First of all, I'll claim that if epsilon is small, then these are actually similar in the sense that e to the epsilon is approximately equal to 1 plus epsilon, and this is by a Taylor expansion. And I recommend you sort of verify this by yourself, but trust me when I say that this is kind of, for small epsilon, these are roughly the same. Of course, you can see that if you set epsilon equal to 10, these will be very different, but for small epsilon, they're comparable. So that says that they're kind of the same. Well, if they're the same, then why do we use this? If they're the same for small epsilon, why do we use this one instead of this one? Well, there's a very convenient fact about the exponential function, which I'm sure you all know, but basically e to the epsilon 1 times e to the epsilon 2. This is exactly equal to e to the epsilon 1 plus plus epsilon 2, the exponent. So the idea is you can just add the exponents when you multiply. And why is that convenient? Essentially, we'll revisit this again later in something called group privacy, but it's essentially saying that, like, imagine you chain this together, like you changed, instead of just one data point, you change 2 data points. Well, you can chain inequalities like this together, and then you will, you can just sort of combine those, and it'll become e to the 2 epsilon rather than, rather than 1 plus epsilon squared. So this is convenient because of this property, which we'll revisit and talk about a bit later. Okay, what else do we want to say? Well, next, I'll comment, this might be obvious or not obvious, I don't know. I'll comment that this definition is symmetric, even though it looks asymmetric. Like, for example, why is it only upper bounded, why is it not lower bounded? Well, it's also lower bounded. It's just written this way succinctly. You can imagine switching the position of x and x prime, and then it'll be symmetric in any way you could probably want. Okay, what else do I want to say? I want to also comment that any differentially private algorithm must be randomized. And yeah, I'm not going to discuss this too much, but take a second to convince yourself that essentially any differentially private algorithm must be randomized if it's non-trivial. And by trivial algorithm, I mean that's one that's independent of the data set. Take some time to convince yourself of that. Yeah, let me comment a little bit more on the randomness here, because it might not have been clear. Like, we're saying that the probability of m run on x is in t. Well, what is this probability over? Like, where's the randomness coming in? Like I said, x, the data set, is going to be sort of worst case. So this is deterministic. There's no randomness in the x itself. The only randomness will be in the algorithm m. It's going to take its input, which is deterministic, and fed into it, and then do something randomized with it, and that'll be where the probability is. It'll just be over the random choices made by the algorithm m. So yeah. And like I said, it must necessarily be randomized, which I've kind of given a hint now for why that is. Okay, there's, I guess, 2 more points I want to make. One thing is, why multiplicative? In the sense that, why do we have this weird notion where, you multiply it by this e to the epsilon? There's other notions of closeness of distribution that we could use. Like, essentially what this says is that the distribution of the random variable m on x is similar to the distribution of the random variable m on x prime. But there's many other ways of doing there's many other ways of arguing that 2 random variables are close to each other. Some include, like, saying that there's total variation, or their statistical distance is small, or maybe their KL divergence is small, stuff like that. Well, we're going to use this one. Other notions, for example, like the statistical distance between the 2 distributions, this turns out to be not very good for privacy, in the sense that the natural way of phrasing it would give rather meaningless notions of privacy. Yeah, I'm not going to talk too much more about this, but I'll refer you to section 1.6 of Salil Vadan's survey in order to read a bit more as to why total variation is not a good distance for privacy. And finally, the last thing we're going to do is sort of talk about the idea of neighboring data sets. What does it mean to be neighboring? I'm kind of going to use in this class 2 different notions of neighboring interchangeably. And for the theory's sake, this is not going to be a big deal. In practice, you might have to actually like sit and think about it and be careful, but it shouldn't be too bad to do in most cases. But okay, I'll use, like I said, these two notions interchangeably. But like I said, neighboring data sets, we might say that they differ in one row, meaning that one way of interpreting this is saying that you take one user's data, so scrolling back up a bit, one user I, say user X1, we imagine that they take their data point and change it to a totally different data point. That's one way of saying neighboring data sets. On the other hand, another sensible way of saying a neighboring data set is what if xi just didn't participate? We're left with the data set just x2 through xn. So there's 1 point removed from the data set. Or perhaps maybe xn plus 1, another individual joins in. Then this would be a case where we added a point to the data set. So there's kind of two notions of privacy, which are kind of, one refers to when we just swap an individual's data, and the other one refers to when we add or remove a single individual's data. The former, where we change one individual's point, is sometimes called bounded differential privacy, and the other case where you add or remove a point is called unbounded differential privacy. So these are kind of the same and they're kind of the not. This might be confusing, but first of all, how are they the same? They're the same because I'll comment that you can view changing an individual's data point as removing that individual from the data set and then adding an individual with the value they should have swapped to. So by that, I mean, there's a factor of 2 in the epsilon that shows up. But essentially, it's just saying you do 2 changes instead of 1 change, and that converts from one to the other. So that's how they're essentially the same up to this factor of 2, which is not a big deal for all theoretical purposes. On the other hand, I claim they are not the same because there's this one annoying little technical fact that, in the unbounded notion of differential privacy, there's the fact that the number of samples n is not known to be private, is not considered to be public data, and your algorithm has to take a varying number of samples, stuff like that. So these are annoying technical things, but yeah, let me just say that we're generally going to be a bit fast and loose with these details, and we're generally going to imagine swapping someone's data just because it's more mathematically convenient. But yeah, if you're implementing these things in practice, you should be very careful about which notion of privacy you're using and what your budget is. For example, it might be possible that you're not doing a fair comparison with another algorithm because they're using bounded differential privacy and you're doing unbounded differential privacy. Okay, so like I said, that's it in terms of technical comments about the definition. It's a tough one, so that's why there's a lot of things we have to comment on. But it's something that you should hopefully get very familiar with over the course of this class. So yeah, that's the notion of differential privacy. Let's do a brief interlude of an alternate way of viewing differential privacy, and that's a sort of hypothesis testing perspective for this. This is a perspective that was introduced by Wasserman and Zhou. And this was from 2010. This is Wasserman is a very well-known statistician, so this is a little bit more of a statistics view on differential privacy. So it's a little bit more operational this time. It's operational in the sense that, what can you do with differential privacy? How do you interpret it, perhaps? But this views it from the point of view of the adversary, whoever is witnessing the outputs of a differentially private algorithm, they're perhaps the adversary. And we view it as the following way. Suppose the adversary is trying to perform a hypothesis test. What do I mean by that? I mean the following, that one of the two holds. So we're told that either H naught holds, where this is the it's what's known in the business as the null hypothesis. So the null hypothesis is saying that the underlying data set is, say, x. So when I say the underlying data set, I mean whatever data set is fed into some algorithm M. And H1, also known as the alternative hypothesis, says that the underlying data set is x prime. So, okay, the adversary is told one of these two happens, and one of these two things holds, and they're trying to figure out which one is true based on the output of M. So based on M, on dataset, we want to decide H0 versus H1. Okay, so intuitively, what can we say? Like, oh, sorry, let me comment one more important thing. I'm saying the underlying data set is x or x prime, and we note that x and x prime are neighboring. Yeah, otherwise this doesn't necessarily make sense. Cool. So we essentially, the adversary is trying to figure out whether they're looking at some data set x or some neighboring data set x prime based on the output of the algorithm that is fed into. So intuitively, what does differential privacy said? Like I said, it basically says that the output of the algorithm doesn't really change much whether it's given one data set or a neighboring data set. That is, the distribution of outputs it produces are fairly similar. So intuitively, what you might think is that this means, let me put this in air quotes, because this is not quite precise, if M is dp, we're going to use dp through this class for a shorthand for differential privacy. So if M is differentially private, then guessing is the best thing you can do. Or rather, like it's close to the best strat. You're not going to get much better if it's like strongly differentially private. So let's say it's approximately equal to the best strat. This is not perfectly true, just because like this imagines, okay, just guessing 50-50 H0 versus H1. But for example, like there's other types of strategies. Suppose they said that every time, no matter what the algorithm output, they say, okay, H0. So they would have 100% chance of success in the case where it's actually H0, but 0% chance of success in the case where it's H1. Whereas the random guessing strategy would give 50% chance in both cases. So you can see that there's like some things which are slightly different from just purely uniformly guessing, but really not that much. So let me try to tell you what an equivalent notion of differential privacy is, based on this sort of hypothesis testing question. So we're going to let P is the probability of this is the probability of saying of the adversary guessing H1 when H0. So imagine the true data set was actually X and the adversary says it's H1. What's the probability of that happening over the sort of random coins of the algorithm, and I guess also potentially what the adversary can do? So this is the probability of making an error in this direction. Those familiar with statistics might know this as a, sorry, I have to be careful. This is a false positive or a false alarm. And why is that? Because, the null hypothesis is kind of the default, and the alternate hypothesis is when something interesting happened. So what we guessed was that something interesting happened, but in fact, it was just the null hypothesis. So that's one notation we'll use. And then suppose we also let Q be sort of the opposite. There's a probability of the adversary guessing H0 when H1. This is sometimes called a false negative or a misdiscovery also. Because you can imagine it should be something exciting happening because we're under H1, the alternate hypothesis. But we said it's H0, which is the null hypothesis. So we kind of missed this discovery, which is kind of a bummer sometimes. Okay, so now that we have the notation in place, essentially what differential privacy says is that these we'd ideally like P and Q to be as small as possible, but differential privacy says that these can't both be simultaneously small. So epsilon dp is sort of equivalent. I claim this is equivalent. We're not going to prove it in this class, but it's equivalent to the following two conditions, that P plus e to the epsilon times q is greater than or equal to 1. And also sort of the other way, which is e to the epsilon times p plus q is greater than or equal to 1. So again, this kind of says that both the false positive and the false negative rate can't be simultaneously small. We've got to make a mistake in one or the other. So let's kind of look at the extreme case where epsilon equals 0, where we have perfect privacy. In this case, it's kind of similar to the sort of setting where I mentioned before, where, for example, we could have random guessing where P and Q would both be 1/2, which would satisfy this inequality. Or we could also have, say, just always guessing H0 would result in Q being 1 and P being 0, which would also satisfy this inequality. So in the perfect privacy case, you can kind of balance these two as however you want. You can choose to have a lot of type 1 errors, a lot of type 2 errors. False positives and false negatives alternatively. But the idea is that this is sort of like a straight line between the two, in the sense P plus Q is always going to be kind of equal to 1. However, this e to the epsilon here essentially lets you get a little bit of advantage in compared to these naive and silly strategies. So it kind of quantifies how much better an adversary could do in terms of this this sort of guessing game. So yeah, this is the hypothesis testing notion of differential privacy, the interpretation of it. And why use this formulation? Well, like I said, one reason is that it's more operational in nature. And by that I mean, like I said, it tells you sort of how much an adversary can actually figure out, like what's their chance of guessing. It's much easier to interpret. It's also useful in terms of being able to other things in differential privacy are facilitated by this. For example, like it allows us to reason about composition of differentially private algorithms. We'll be talking about this a bit later, but essentially this is used by Kairuso and Vishwanathan in order to optimally quantify how much it costs to ask several queries on the same data set. And also it's been used to formulate other notions of differential privacy, which we'll probably talk about a bit later in this class, including, say, Gaussian differential privacy, which is a rather recent notion by Dong, Roth, and Su, which is like last year. I think it's published this year, but yeah. Okay, so that's an alternative notion of an alternative perspective and formulation of differential privacy. But this is just sort of for your own interest. If you're curious, you can check out these papers and Wasserman Zhou's original paper. For this class, we'll be focusing more on this sort of more common definition, more common formulation, rather. Okay, so that was technical for a while. Let's take a step back and talk a little bit more and say, what does differential privacy mean? How do we interpret a meaning of differential privacy? What does it tell you and what does it not tell you? What does it guarantee and what does it not guarantee? So let me repeat sort of what the in English notion of differential privacy. Let me even write it down because I think it's very important. It says that differential privacy implies that the probability of any event is comparable whether or not an individual is in the data set. And this very simple way of stating it, we can immediately see that this will be useful for a number of reasons. It essentially says any sort of bad thing that can happen to you is not much more likely if you participate in the experiment or this algorithm compared to if you withheld your data. So, for example, let's see how this rules out attacks. Yeah, and it's just basically by using this type of property. Like, for example, linkage attacks, where somebody finds another data set and tries to match it with individuals in the private, based on the outputs of the algorithm run on the sensitive data set. Well, because of the fact that whatever it outputs has a similar probability of coming out whether or not you were actually in the data set, you can essentially reason that, again, the probability of this bad outcome happening, which is somebody effectively manages to link you to something, is sort of very similar to the case when you're in the data set, when you're not in the data set. And I guess depending on how you think about it, maybe the chance of them being able to identify you if you're not in the data set should be rather minimal, let's say. I can imagine some cases where maybe they could by accident get you, but yeah, essentially this type of linkage attack is ruled out. And it's the case even in for past data, whatever data might exist, but also future data releases as well. This is an important part that differentially private data releases in some sense future-proof. Okay, besides linkage attacks, it also prevents against reconstruction attacks. And in some sense, it matches the attacks that were shown in Denur Nassim. We'll quantify this better in a later lecture, essentially talking about composition. But in some sense, differential privacy up to a certain number of queries with a certain amount of noise will prevent any sort of reconstruction attack, in a rather strong sense. But then there's going to be a sharp threshold where it goes from these attacks being prevented to not really having privacy at all. You can get this sort of blatant non-privacy. And the last thing I'll say is just basically arbitrary risks. These are just a few examples, but I really want to stress how powerful this is. Once again, it's using the fact that essentially whatever would have come out is only a little bit more likely than in the case where you weren't in it. So this only bounds the probability. This says the probability of something bad happening to you by participating in this experiment is not going to increase by much. Maybe if epsilon equals 0.1, then it says maybe by 10% more a chance of a bad event happening to you. Cool. So that's what differential privacy does. But what does differential privacy not do? And this is something which is very frequently, I think, misunderstood. Because people sometimes get confused about this. What doesn't DP guarantee? And the crucial thing is differential privacy allows you to do statistics in machine learning. So this is kind of what it allows. So this is kind of not what it rules out. So in particular, you can learn things about, you can in some sense learn things about a population without being a privacy violation. For example, there's a very common example which is mentioned, which is the smoking causes cancer example. So for this, imagine there's an individual who smokes cigarettes and is choosing whether or not should I participate in a study on trying to measure correlations between smoking and cancer. They know that a positive result in the study would be bad news for them. Why is that? Because, maybe their insurance company knows that they smoke, and therefore they can say, okay, you're smoking, therefore you're more likely to incur cancer, and therefore it's your own fault, so we're going to raise your premium. Essentially, this individual would not want a positive result to come out of the study. So they're weighing the risks. They're wondering, should I participate in the study? Not sure. They're told that the study is going to be differentially private, and so that assuages their fear. They're thinking, okay, they're doing the study differentially privately, so my data doesn't matter. They're going to somehow hide my contribution, and that'll be okay. So I'll participate. So the person participates in this study. It comes out that smoking causes cancer, and his insurance company will now increase his rates. So this is the bad outcome that he wanted to avoid, right? But maybe he should have stayed out. So the question is this a privacy violation? And the answer is that no, it's not a privacy violation, because this is kind of what we want to do statistical analysis or machine learning in the first place to do. We want to infer something about the population, and that might allow us to infer things about individuals. So kind of what we learned in the study might be that if you take an individual from the population, say you take a random individual and they smoke, then it's likely to cause cancer. However, because this individual in particular smokes, then it allows you to infer that they may have cancer, or it might cause their cancer. Now, let me just, what do I want to emphasize? Why is this actually private? The claim is that essentially this individual's participation in the study did not actually change the probability of this outcome happening that much. Like I said, the probability, like a user participating can only increase the probability of whatever outcome happening by a certain amount. So essentially that means that even if they didn't participate, then it would still probably say that smoking causes cancer. So indeed, it fulfilled the promise of differential privacy, but the thing is, differential privacy allows you to still learn things about a population. It won't necessarily tell you about that particular individual there, whether they in particular will catch cancer or not, but it allows you to say something sort of at a broad level. Cool. So this is a little bit of a subtle point, so maybe think about it a bit more. I've linked also some other readings which sort of discuss this in more depth as to what differential privacy does and does not allow. Okay, there's sort of two other comments I want to make. Yeah, let me say next that it's not for individual use in some sense. Let me not for individual level like learning, let's say. By that I mean, if you want your algorithm to output a single individual, like it basically says, okay, here's a set of data set, here's a data set, and we want to pick an individual who's the person we should have for our drug trial or something. That's not really something you can do with differential privacy. It's not intended for that purpose. It's a somewhat different, perhaps, notion of privacy, because if they're not even in the data set, then there's no chance that you would ever output them as a candidate. It's just sort of a type mismatch. To bring up one timely example, like this, let me mention, for example, COVID-19. One thing that people say is, okay, we need to be able to do privacy-preserving contact tracing, respecting individual privacy in some way. Well, I'm not going to get into what privacy means there, but it definitely does not mean differential privacy, a very different notion of privacy that we mean there. And why is that? Because, differential privacy sort of says, if they weren't in the data set, you shouldn't be able to figure, it shouldn't make a difference on the outcomes. But when you do contact tracing, you really want to figure out, where an individual went and who they met with, met with individual X, Y, and Z. that's something you really want to figure out. So it's a type mismatch for that sort of thing. However, it can still be useful in some of these types of settings where, for example, aggregate level contact tracing could be a sort of application here. And by that, I mean, perhaps there was some event, some big conference or something, and maybe you can differentially privately analyze how many people at this had COVID-19. And if it's sufficiently high, then you send an alert to everyone at the conference saying that, okay, just a warning that you were at you were at an event with a lot of people who had COVID-19. That's the type of thing that it would be okay for, but not for the previous individual level thing. Let me note along the lines of this latter aggregate level tracking of location to try to understand things. There's actually a product released by Google, like some community location insights, which kind of says which places have been more and less trafficked since COVID-19 struck, and they use differential privacy for that release. I've linked this. I've dropped a citation in the notes, so you can check that out. And a final thing that I'll mention is that differential privacy is information theoretic. What do I mean by information theoretic? I mean that, this is not really dependent on the adversary being computationally bounded or being bounded by, what information they have on hand. This is really just a 100% information theoretic guarantee, even if they were sort of infinitely powerful. This is very different from the case of security, where often we do things based on computational hardness, based on hardness assumptions, saying that no adversary can solve this type of problem computationally efficiently. For example, public key cryptography is based on assumptions very similar to saying that, like, if there's a very large number, then it takes a long time to factor it. In contrast, this is not based on computational assumptions. This is sort of information theoretic, and no matter what sort of power they have, it's impossible to distinguish. So there has been some work on looking at, computationally bounded adversaries in differential privacy, and I've linked this in the lecture notes in case you're curious. But generally, we're going to focus on the information theoretic notion. Cool. Yeah, with that, let's finally conclude by revisiting randomized response now that we have, a good understanding of what differential privacy is. So differential privacy, it frequently uses, it has a few building blocks, things like randomized response and a few algorithms we'll talk about in the next class. The cool thing about differential privacy is many of the algorithms you can build out of just a few basic primitives like this. So it's important to have them in hand and have a good grasp on what they are when you're designing a new algorithm. So let's revisit randomized response and show that we have the differential privacy guarantee when our algorithm M is randomized response. So let's say M equals like gamma randomized response. How dp is M. Remember, it's a property of the algorithm. So let's try to analyze how private it is. So in fact, going all the way back, what is randomized response? Essentially where the individual, each individual sort of flips their bit and they send the message yi, even if their private data is xi. So what we're going to do is we're going to analyze differential privacy of this string. So, like, in particular, we're going to suppose M outputs, instead of saying, we're just going to say it outputs at y1 through yn. Recall when we were talking about it earlier, we were saying that that it outputs, some function of these yi's, but it's in fact possible if you show that this is differentially private, then something called post-processing will allow us to argue that any function of this bit string y1 through yn is also differentially private. So we're just going, we'll revisit this in the next class, what post-processing is. But for now, let's just say we want to output y1 through yn and say how differentially private is that exactly. Okay, so we're going to consider one particular outcome and then a generic outcome. So consider the bit string, consider the realization a, which is in, say, 0, 1 to the n. And what is the probability that m outputs this bit string? Well, the probability that m on some data set is equal to a is equal to the product of probability that yi equals ai. And why is this? This is just saying that, this is because these bits are all independent. Each sort of individual will flip their own coin independently. So therefore, we're just going to take the product of all those probabilities, and that's how we get out the overall probability of seeing mx equals a. So what are we going to do? We're going to suppose that x and x prime differ in coordinate j. So like I said, x and x prime are neighboring databases. So we're going to say that they differ in, say, coordinate j. Everywhere else, it's equal. Now, recall that differential privacy looks at the ratio of the probabilities. So let's just write it out and see what happens. So what's the probability that m on x equals a divided by the probability that m on x prime equals a? Well, just substituting this in, we'll see the ratio here. So this is just going to be the probability that yi equals ai, as we had before, and divided by essentially the same thing, except with y prime I here. Now, the convenient thing is that almost all of these terms will cancel because they differ in only coordinate j. So this is going to be equal to probability that yj is equal to aj divided by probability that y prime j equals aj. Okay, now let's just recall what these values are. Well, this is going to be just writing out randomized response again. This is going to be with probability 1/2 plus gamma, and this with probability 1/2 minus gamma. Now, we're trying to recall that we're trying to prove an upper bound on the ratio of any two probabilities. So we're just going to see how big this can be. And the biggest it can be is if the sort of bigger value is in the numerator and the smaller value is in the denominator. So this will be 1/2 plus gamma divided by 1/2 minus gamma. And so this is like, I guess technically we could stop here and we could say that m is the natural log of 1/2 plus gamma over 1/2 minus gamma dp, but that's not very satisfying. In fact, let me say that, let me say that gamma, say, less than or equal to 1/4. If that's the case, then this implies that this quantity here, 1/2 plus gamma over 1/2 minus gamma, is less than or equal to e to the o of gamma. So this is kind of this is not too hard a bound to see or to show. Just like do the Taylor expansion once again, and you can verify it. But this implies that m is O of gamma differentially private. And in particular, if you set, gamma to be epsilon, then you'll have O of epsilon differential privacy. Okay, so let's recap what we have shown here. So we have that. Let's substitute an epsilon. In fact, say epsilon randomized response. This is epsilon differentially private. And this is just recalling from earlier the accuracy in terms of how well it allows us to estimate, say, p tilde minus p is less than or equal to O of 1 over epsilon times square root n. Okay, so that's not bad. We have a privacy guarantee and an accuracy guarantee. These are both things we're going to want when we're doing private analysis of algorithms. Two comments are in order. One is that I was a little bit sneaky with you. This is not just epsilon differential privacy. There's actually a stronger notion of privacy, which we're going to revisit, I guess, later in this class, which won't be our main focus. It gives you epsilon local differential privacy. In that, the sense that, each individual sort of flipped their own data. They didn't require the curator to do it for them, so they don't even have to trust the curator. So there's a stronger notion of privacy than we're going to be focusing on for a lot of this class, but in particular it assumes this, regular, just epsilon differential privacy. The other thing I'll comment is that this accuracy is pretty good. It's a good starting spot, but it's not the best accuracy we can hope for. In particular, this square root shouldn't really be here in the sense that if you just want epsilon differential privacy, you can get rid of that. So this is where we're going to end for today, but essentially we're going to start next class with what's known as the Laplace mechanism or Laplace algorithm, which is an example of it's kind of like differential privacy 101. This is like the bread and butter algorithm, which is very useful. It's very broadly applicable, also achieves epsilon differential privacy, and will achieve a better accuracy for this sort of mean estimation problem, let's say. So yeah, this is a very important one, and we'll cover that in the next class. Thanks for watching today.